Thank you. I'd like to first of all thank Codina for the invitation to come to this program. It's always a pleasure to be at the Newton Institute, and Codina's been very helpful. And also I want to thank Tyler. Where's Tyler? Yeah, because this work that I'm going to be talking about really originated from conversations that I had with Tyler starting 5 years ago in 2019 that continued for a year or two. And he brought to my attention some papers in the physics literature about the fact that in high-dimensional critical phenomena, first of all, there was a kind of a debate as to what was the size of the susceptibility in finite size scaling, depending on the boundary condition. And also that with periodic boundary conditions, there was a plateau in the two-point function, which is the main thing that I'm going to be talking about here. And it's high-dimensional critical phenomena, so it's purely a high-dimensional phenomena that I'm talking about, which means above the upper critical dimension. And I'll be talking about self-avoiding walk, spin systems like the Ising model and phi to the 4, as well as percolation. This phenomenon occurs in all of these models. And the talk is based on collaborations with these people. So Tom Hutchcroft, who's a professor at Caltech, Yu-Cheng Yu, who you heard from yesterday, is a PhD student at UBC. Manuel Mishta got his PhD from UBC in November. He's now working in the finance industry. Roman Panis is a PhD student in Geneva, who will defend, I think, in a few weeks. And Jiwoon Park got his PhD here last year at Cambridge, and he's now back in Korea. So the torus, you should think about as being like a box in ZD. It's always discrete. It has side length r, so r vertices on each side. R to the d is the volume. And so I'm interested both in what I'll call free boundary conditions, when this is your entire graph, or periodic boundary conditions where there's like a row of edges along the right-hand side and along the top, which join up to the other side to create the torus like this. And I'm interested in what happens as r goes to infinity, so the size of the torus is increasing. And with d at or above the upper critical dimension, which is 4 for self-avoiding walk and spin systems, or 6 for percolation. And I've got like half a dozen examples to talk about. So I won't be getting into details of proofs, but I want to try to describe the general phenomena and see how one model is related to another and so on. So example 0 is not a great example, but it shows something. So simple random walk on the torus in dimension greater than 2. So let's define the n-step transition probability to go from a point 0 on the torus to another point x, and fix some z, which is between 0 and 1. And define this two-point function, c sub z of x on the torus, is the generating function for the sequence Pnx. And it has the interpretation as the expected number of visits of a random walk to x for the walk which is killed at a random time n, which has this geometric type distribution. So the z to the n there is the probability that the walk is still alive at time n. The susceptibility in this model and in all the other models I'll be talking about is defined as the sum of the two-point function over the torus. In this case, we'll also be looking at ZD, but here it's the torus. And you can do the sum. When you sum over x, Pn of x, you get 1, so it's just a geometric series, and the sum is 1 over 1 minus z. And that's equal to 1 plus the expected killing time. So the expected killing time and the susceptibility are essentially the same here. And the idea is that if, we've seen in a previous talk that the mixing time on the torus is of order r squared. And the idea is that if the expected lifetime of the walk, or the susceptibility, is much greater than r squared, after r squared steps, the walk is basically uniformly distributed over the torus. And so it's going to spend amount of time chi, which is expected lifetime, divided by r to the d at each site. And that idea is captured in this theorem, which it's actually an older theorem than this, but it took years for it to finally be published in 2024. for d greater than 2 for x a torus point, and for in this range where the expectation, where the susceptibility is large, the difference between the 2-point function on the torus and the 2-point function on ZD, and here I didn't mention it, but let me go back to that previous picture. I'm going to sometimes think about the torus as being this box. So the origin is like a point in the center of the box, and x is like a ZD point in the box, and I'll use that as the address also for a corresponding torus point. So that's happening here. This x is in the torus, even though I'm evaluating it on this function, which is defined on ZD. The difference between the finite volume 2-point function and the infinite volume 2-point function is given by this chi over RD asymptotically as R goes to infinity. So it's chi over the volume, the susceptibility divided by the volume. And in particular, for d greater than 4, if I look at this range of Z here, this torus, this chi is 1 over R to the D over 2. Sorry, it's R to the D over 2. And so this ratio is 1 over R to the D over 2, 1 over the square root of the volume. And the 2-point function has a plateau in this case. So it's behaving like the infinite volume one, but then there's a constant term, and in dimensions bigger than 4, the constant term will win as soon as x gets large enough. So this is some fractional power of R when d is greater than 4. So it's behaving like the infinite volume 2-point function, and then it flattens out. So I want to look at something related in a very simple example of self-avoiding walk on the complete graph. So the complete graph, as you know, is a set of, in this case, v vertices, which are each pair is joined by an edge. And it's very easy to count the number of self-avoiding walks on the complete graph that start from 0. You've got v minus 1 places to go for your first step. Now you've used up 2, so you've got v minus 2, v minus 3, and so on. And so it's this falling product. It's the kind of thing that appears in the birthday problem if you teach probability. And then the susceptibility is the generating function for this sequence. And I'm normalizing. This is the convenient normalization for Z. So if you stare at this long enough, and maybe look in the literature a little bit, you can find that this is, apart from some prefactor, given by the incomplete gamma function. So it's exactly solvable. And if you then go to the literature about the incomplete gamma function, you will find perhaps even more than what you want to. So there's a great deal there. And so this theorem is just a combination of this observation and looking at what this gamma function does. And there are 3 phases. Well, there's 2 phases separated by a critical point. So if Z is less than 1, the susceptibility is finite, and it behaves like 1 over 1 minus Z as the volume goes to infinity. If Z is greater than 1, then it behaves in this way, and the thing to notice here is that this function log Z plus 1 over Z minus 1 is positive when Z is greater than 1, so there's exponential growth of the susceptibility. Whereas at the critical point, Z equals 1, and I'm kind of zooming in here and looking in a critical window which has width 1 over the square root of the volume. If I take Z to be 1 plus S over the square root of 2 times the volume, then this susceptibility is asymptotic to the square root of the volume times this function, which I want to call the universal profile for self-avoiding walk. And it's given by this formula. So f of s is given by this formula. This is also a function that you can look up in the literature. It's related to something called the Faxon integral, and many of its properties are given, for example, in the book by Frank Olver on asymptotic expansions. Anyway, this function. Here's the s. So in the critical window, I want to look in this critical window and look at the 2-point function. Now, the 2-point function for self-avoiding walk on the complete graph is rather simple because all the points other than the origin are basically the same. And so the 2-point function, which is requiring now in this generating function the walk to end at x, whereas we didn't care where it ended up here, it's just 1 over the volume times the susceptibility. And so it behaves as 1 over the square root of the volume times this profile. That profile is going to come back again later. You don't have any 1 over x to the d minus 2 type term here. It's just the plateau term that appears. The 2-point function is basically constant. The constant is 1 over the square root of the volume, and there's some universal profile in the window. So let's look at a harder problem now, which is weakly self-avoiding walk on the torus for d greater than 4. I want to study the torus problem by using things that I know about ZD. So let me first review some of our knowledge about what's happening on ZD. So the 2-point function is the generating function for this Cn of x. Cn of x is given in terms of a parameter lambda as the sum over all walks of length n from 0 to x. These are usual nearest neighbor paths in the lattice from 0 to x in ZD. And there's a penalty for self-intersections. So we saw this in Yucheng's talk. So any pair ST where the walk is at the same time at those, so walk is at the same location at those times will incur a penalty 1 minus lambda. So if lambda is 1, self-intersections are just completely ruled out, and you have the strictly self-avoiding walk. And if lambda is not 1, but it's positive, then you're in a weakly repelling situation. So let the susceptibility be defined as the sum of the 2-point function. So that's just if you sum over x here, you just get Cn. That Cn of ZD is the sum over x of this sequence up here. And the 2-point function and the susceptibility have a radius of convergence, which is given by this limit, which exists by elementary subadditivity argument. So there's a finite radius of convergence. This is finite. Well, now there are many theorems that go back to the work of Bridges and Spencer in 1985, and Hera and I played a role in that. And for lambda small, that was first for Bridges and Spencer, but also for lambda equals 1 with Hera, and for d greater than 4, we know from the Lace expansion that the critical 2-point function has this Gaussian decay. The susceptibility has this linear divergence. Cn behaves purely exponentially without any power law correction. And if you use diffusive scaling on your walk, then you end up with a limit being Brownian motion. Okay, so that's been known for a long time. A new ingredient that does not follow from any of this, which has actually required some new ideas, including a new convergence proof for the Lace expansion, is this near critical decay. So we've seen examples of this kind of decay in previous talks. It says that for d greater than 4, for x in ZD, I'm still on ZD, and for z less than or equal to this critical value, the 2-point function is bounded above by a multiple of what it's doing at the critical point, which is exponentially decaying with a rate which is square root of the deviation of ZC from Z. So this is the correlation length exponent here, 1/2 that's showing up. So I did this for the weakly self-avoiding walk, and then Yucheng extended it to the strictly self-avoiding walk using these kinds of results. Now, an immediate corollary of that is an upper bound on the 2-point function on the torus, which is related to what we saw earlier for simple random walk. And maybe I'll just show you a little drawing here. So this is supposed to be the torus, and I'm looking at a walk that starts at 0, and when it goes off the right-hand side, it comes in the left, and goes off the bottom, it comes in the top. So it's a walk from 0 to x. Those walks can be lifted to ZD. So if you have a walk on the torus, you can always lift it to ZD. And the lift looks like this. You just draw copies of the torus box. You pave ZD with those copies. And instead of going off to the right, you go to the next copy. So, and so on. So there's a correspondence between walks on the torus and these lifts. And because of that, you get this inequality which says that the 2-point function on the torus is bounded above by the sum of the 2-point function on ZD for a walk that goes to a representative of the torus. So this walk ends at x, this one ends at some x prime, which projects back on the torus to x. So this sum over RU is like summing over all of the different things that x prime could be when you lift this walk up. And it's an inequality because here there was a self-intersection, for example, in this walk on that red dot that would have incurred a penalty 1 minus lambda, whereas once I've lifted the walk, that doesn't happen, and so it's just 1. So you get this inequality. In other models, this inequality is not so straightforward, but in this self-avoiding walk problem, it is. And then I'll separate out the the u equals 0 term here, which is just the ZD 2-point function, and then use this inequality for the others. And so I leave out some steps here, but basically you just plug in this inequality and change the sum to an integral, and the integral turns into this. X doesn't really play a role, because RU is a lot bigger than X. And this square root of the susceptibility that's appearing here is just this ZC minus Z to the 1/2, because the susceptibility is diverging linearly. And so this is, if this was 0, the integral would blow up. It's not 0, and so the integral, actually, you can evaluate its asymptotic form, and it behaves like this. So you get this upper bound, which is like the one that we saw before. The torus 2-point function is bounded by the ZD 2-point function, plus a term which has the susceptibility on ZD divided by R to the D. So this is not an interesting inequality when Z is ZC, because then the susceptibility is infinite, but for Z less than ZC, it's telling you something. And there's a complementary lower bound. So for D greater than 4, for X in the torus, and for Z in this interval. So basically you should say, I'm away from the critical point by, I'm close to the critical point by at least R to the minus 2, but I'm away by R to the minus D over 2. So D is greater than 4, so this is a non-empty interval here. And in that interval, the 2-point function on the torus is bounded below by the 2-point function on ZD, plus a small constant times chi over RD. So the way that that's proved, you kind of get the idea, what have you lost, what did you give away here when in the upper bound? You gave away this kind of situation here where you lost the 1 minus lambda because of those 2 red boxes there. And a simple inclusion-exclusion argument tells you that you can, to prove the lower bound, it's sufficient to get a bound on this quantity here. So here T is this sum that appeared in the upper bound. So there's T minus G is just the chi over R to the D as an upper bound. So that's just a constant. So basically you just have a convolution of this T with itself, and using the upper bound for the near critical behavior, you can compute that. And this is a diagrammatic representation. So the solid lines are the T's, and the dotted line is the T minus G. Yes?
Y minus phi, right? Is it the X minus?
No. So these 2 points on the torus are the same point. They're the point Y.
Okay.
Yeah.
So that's
This is a torus sum. Yeah. So it's kind of been projected down to the torus, but the T has the sum which goes outside the torus. Now a corollary of this is that if you take a torus point and let Z star be the top of this interval, which I want to refer to as the bottom of the window, because I'm expecting to have a window around ZC, the infinite volume critical point of width 1 over R to the D over 2. And so we're at the bottom of that window, so to speak, here. But if you, the susceptibility we know is R to the D over 2, and so we get this behavior using the usual asymptotic behavior of the critical two-point function for ZD. And if you sum this, you find that the plateau term wins. When you sum this over the torus, you get r squared, and when you sum this over the torus, you get r to the d over 2. So this shows, by the monotonicity of the two-point function in Z, that at ZC, there will be a plateau. Now, if you compare this with free boundary conditions, that is, where the walk has to be confined to the, to the finite box without any periodicity, then it's clear that the free boundary condition two-point function is bounded above by the ZD1, because the ZD1 just has more walks, and that one behaves like 1 over x to the d minus 2. So for free boundary conditions, there's no plateau, but for periodic boundary conditions, there is. Now, on the complete graph, we found that in that window around the critical point of size 1 over square root of the volume, there was this profile playing a role. And so I propose here a conjecture. I have more evidence for this, which I'll discuss later, that says that this profile plays a role also for the weakly self-avoiding walk on ZD for d greater than 4, or on the torus, TD for d greater than 4. So here's the conjecture that for any real s, positive or negative, and x in the torus, the two-point function in the window, so this ZC plus SWR is meant to be in the window. The WR is r to the minus d over 2, but with a specific log correction for d equals 4, is asymptotically given by the infinite volume two-point function at the critical point, plus a plateau term, which has some constant, 1 over r to the d over 2 with a log correction for d equals 4, times this specific profile for the plateau amplitude. So I'll come back to this later. Now let me ask a related question, which is, how long does it take for a torus weakly self-avoiding walk to figure out that it's on a torus and not that it's on ZD? So here's a theorem with Emmanuel Mishta about that. So for d greater than 4 and lambda small, so we're really talking about the weakly self-avoiding walk here. This theorem has not been proved in a strictly self-avoiding walk setting. If the length of the walk is less than the square root of the volume, then with the same amplitude and ZC from ZD, so these are ZD numbers that are appearing here, the torus Cn behaves like that ZD Cn times some explicit correction. And so if n squared is less than r to the d, then if it's relatively small, then this will be absent. So the proof is a long story. It involves the lace expansion, a coupling of weakly self-avoiding walk on ZD and the torus, and a detailed analysis of the torus susceptibility, followed by a Tauberian theorem to extract the coefficient of the susceptibility, which is what this Cn is. The Tauberian theorem is basically the Cauchy integral theorem in this setting, so we have to go to complex values of Z. So here's the theorem again. And for example, if you take n to be r to the p with p between 0 and d over 2, then so p is less than t over 2, then the torus Cn behaves exactly the same as the ZD Cn. Yes?
Sorry, what was beta? Beta is lambda?
Oh yeah, no, beta is lambda. Yeah, thank you. Right, so in that sense, we can say, well, the walk doesn't know that it's on the torus. A conjecture that we haven't proved and don't know how to prove is that if n is approximately, if it's comparable to r to the d over 2, square root of the volume, then Cn will remain like Zc to the minus n, same size as it is here. But if n gets larger, then Cn will get smaller, because the walk is going to be sitting on top of itself so much that all those 1 minus lambdas are going to start piling up, because the walk has nowhere else to go. Here's an interesting theorem due to Emmanuel Mishta. It says for a torus weakly self-avoiding walk, so lambda small here, do the diffusive scaling on the walk for a walk that lives to length r to the p, where p is somewhere between 2 and d over 2. Then this xr, I've written xn there, that should be an r, xr converges to Brownian motion, an infinitely long Brownian motion on the continuum torus, with the same diffusion constant d that we know is the case for weakly self-avoiding walk on ZD. So in other words, if you take the lift of a torus weakly self-avoiding walk of length r to the p, where p is between 2 and d over 2, that'll converge to Brownian motion on RD with the same diffusion constant as seen for weakly self-avoiding walk on ZD. So that's another sense in which walks of this length do not know they're on a torus. All right, so let me move on to example 3, the Ising model. So I think I probably don't need to spend a lot of time introducing the Ising model here. You have a finite box in dimensions greater than or equal to 2. The volume is r to the d. You can look on either free boundary conditions where you just have spins in the box and they don't interact with the outside world at all, or periodic boundary conditions where the boundary wraps around. And you have a spin configuration for those sites in the lattice, sigma x, which are either at -1 or +1, and at an inverse temperature beta, we've got the usual probability distribution. Expectations are denoted in this way. Beta is the inverse temperature, and for high temperature, so here these are 3 pictures with different values of the temperature. So for high temperature, well, in all of the pictures, the top of the box is white, and the bottom of the box is fixed to be blue. And you see that the boundary conditions basically don't penetrate into the bulk for high temperature, whereas for low temperatures, they cause a phase separation, and right at the critical temperature, something interesting happens. So let's define the 2-point function either on ZD or with free boundary conditions or with periodic boundary conditions to be tau. So it's sigma 0, sigma x. Expect the correlation of the spin at 0 with the spin at x. The susceptibility, as always, is the sum of the 2-point function. And there's this critical value, and that's the critical value for the infinite lattice. And I also introduced this quantity, which is called the renormalized coupling constant. So it's in terms of the total magnetization, sum of all of the spins. It's basically minus the truncated 4-point function. So there's the fourth moment minus 3 times the second moment squared normalized. Due to correlation inequalities, this always lies between 0 and 2. It's 0 if S is Gaussian, and it's 2 if S is constant. And it's always in between otherwise. So here's a theorem with Yucheng and with Roman Panis, just appeared on arXiv in May, that for d greater than 4 and for x in the torus, we have upper and lower plateau bounds on the torus 2-point function. So here we're looking at the upper bound. So we've got the torus 2-point function at x here. It's bounded above by the infinite volume 2-point function plus this plateau term, which again takes the form susceptibility divided by square root of the volume. And there's a lower bound in a similar kind of interval to the one that we saw previously for weakly self-avoiding walk. There's an r to the -2 here and an r to the -d over 2 here. That's smaller. And we have a lower bound which matches the upper bound. And in particular, if we call beta star this value here, which is sort of the best beta that we can handle, then we see that because of the asymptotic behavior of the 2-point function, we get that the torus 2-point function at beta star is comparable to 1 over x to the d minus 2, the Gaussian term, plus a plateau term, and the torus susceptibility, which you get by summing this, is dominated by the plateau and gives a value r to the d over 2. Not only that, we show that there's a constant CG such that this renormalized coupling constant at beta star is not 0. It's bounded away from 0. So that means that we've got a non-Gaussian limit on the torus. If you compare this with free boundary conditions, there's a recent result of Kamiet, Zhang, and Newman. I mean, the upper bound is easy. The lower bound requires work. It requires you to stay away from the boundary a little bit, actually. you have this just 1 over x to the d minus 2 behavior, and the susceptibility is like r squared. So the 2-point function has, again, a plateau for periodic boundary conditions, but not for free boundary conditions. Now, the main input for the proof, or a main input for the proof, is a very recent result of Dumesnil-Copin and Panis. This doesn't use the Lace expansion. There is a Lace expansion for the Ising model due to Akira Sakai, but that's not being used here. They are using random current representation and some rather clever reflection ideas that for d greater than 4, no small parameter, the ZD 2-point function is bounded above by this near critical. So this is exactly the same form that we had for the weakly self-avoiding walk that was so useful in generating the upper bound on the Torus 2-point function via this lifting argument. That same bound holds with the same square root. That's the exponent nu is 1/2. And they also have a lower bound for this range of x, which when beta is equal to beta c is all x. It's bounded below by 1 over x to the d minus 2. So we use this heavily, together with the random current representation of the Ising model, and a new coupling of the Ising model on the torus and ZD. We were inspired in this by work of Papathanakis, but he had some good suggestions as to how to proceed in this problem. So the upper bound comes from an inequality just like the one that we had before, but here you have to actually do some work in order. It's not just a simple lifting argument like this. You need to work with the random cluster and find a way to kind of couple the random cluster on the torus with the random cluster on ZD, and that's actually a fairly serious endeavor. It takes up a fair part of our work. But once you've got that, then you can just substitute in this upper bound into the sum and do the integral the same as before, and you get the same plateau upper bound for the torus 2-point function. I won't try to explain why this is the right diagram for the lower bound, but there's again a kind of inclusion-exclusion type argument that you use to say what did I lose when I used this upper bound, and that so what you lose, you need an upper bound on that, and it's given in terms of this expression here. Pi is the projection from ZD to the torus. It has this diagrammatic form. If you're at all used to these diagrams, you may know that the bubble diagram is finite above 4 dimensions, and effectively this bubble here of solid lines shrinks to a point, in which case you get the same diagram that we had for the self-avoiding walk problem. We have a lot of conjectures. So define the universal profile to be the second moment of this measure on R. So this is a measure on R. X is a real variable here. That's the Lebesgue measure. And, well, it looks, we've seen this before for the self-avoiding walk. And define the window scale to be r to the minus d over 2 for more than 4 dimensions. And there's a logarithmic correction, a specific one that is present for 4 dimensions. Then our conjecture is that the torus 2-point function in the critical window, so at beta c, that's the infinite volume critical point, plus a multiple s of the window size, is given by the critical infinite volume 2-point function plus a plateau term, which is r to the minus d over 2 with a log correction for d equals 4, multiplied by this profile. So this is where the s dependence comes in. The s is the scaling away from the critical point within the window here, and it's explicit. Moreover, if you take the limit of the renormalized coupling constant, you get this explicit form, which has the property that as s goes to minus infinity, this right-hand side goes to 0, so that's saying you're moving into the Gaussian regime, whereas for s goes to plus infinity, you're moving into the most non-Gaussian regime that you can. 2 is the biggest that this can be. So I will motivate these conjectures subsequently. that will come from the phi to the fourth model. So in the phi to the fourth model, it's kind of a close relative of the Ising model. Again, you have this finite box, lambda r, which could have periodic boundary conditions or free boundary conditions, whatever you like for the moment. And I'm looking at the n component model. So to each point in lambda r, I have a spin which is a vector in Rn. Okay, so it might be real, but it might be R2, it might be R3. It's up to you. Any n greater than or equal to 1. And then define a Hamiltonian. So I want to think about G as being fixed. We can only handle G small in our theorems. It's fixed and small. And nu is a variable which plays the role of temperature. And we define this Hamiltonian. So there's this usual kind of kinetic term here which involves the Laplacian on our graph, lambda r. And then there's a potential term. And the potential depends on G and nu, these two parameters. So as I say, G is fixed. And nu we want to vary. And I'm really interested in the case where nu is negative so that this is a double well potential. And it looks like this. Okay, so a single term here graphed against the modulus of phi x would have this double well shape. And when you exponentiate it, as you want to do in the Gibbs factor, it'll have two peaks. So if in the case n equals 1, what this is telling you is that the spin wants to be either here or here. It's kind of like a generalization or a smoothing out of the Ising model. You can get the Ising model by taking an appropriate limit of this. So here's the Gibbs measure. There's a partition function as usual, and it's the integral over phi x for each x in the lattice. So it's an integral over Rn for each lattice point, and there's the Hamiltonian there. And we define the two-point function as the correlation between the spin at 0 and the spin at x. And a good convention is to put a 1 over n there, where n is the number of components. And the susceptibility is the sum of the two-point function. Now, for the case of Z4, on the Euclidean lattice, there's an extensive literature on this, which uses rigorous renormalization group methods to compute critical exponents, most of the ones that you would want to compute. So gamma, nu, eta, alpha, delta, if you know what those exponents are. And most of them have logarithmic corrections. And so these people were involved in that over the last decade. And so there's a lot of tools. Now, the tools are heavy. And we wanted to investigate this finite size scaling type problem and decided not to be in the most difficult situation from the get-go. So we worked with the hierarchical model first. As I'll argue, the results, the conclusions that we draw from the hierarchical model, we believe hold verbatim for the Euclidean model, but that's not proved. So what is the hierarchical model? Well, you see it here, that you have a kind of a hierarchy of blocks. 0 blocks are points. A 1 block is an L by L by L, however many dimensions you have, block. In this case, L is 2 and D is 2 in the picture. 1 blocks are arranged into 2 blocks. So L by L by L, 1 blocks form 2 blocks, and then you increase to 3 blocks, and then you would duplicate this 4 times. You would have a 4 block, and so on. Hn consists of a single n block. Now, I want to think of that n block as actually sitting in an orthant of Zd. Okay, so this is like, this corner down here would be like the origin of Zd, and this is sitting inside the first orthant. And you can go on forever with this and look at h infinity. And for x equal y on h infinity, define jxy to be normalized so that it sums to 1 for any, when you sum over 1 for any fixed x. L to the minus jxy to the d plus 2, where jxy is the smallest scale with x and y in the same block. Okay, so the first time x and y are in the same block, so like if this was x and this was y, jxy would be 3. And then on Hn, so on a single n block, I want to try to mimic periodic boundary conditions. So I want to think that I've got my n block, and then I'm going to have lots of other n blocks which are paving H infinity, and I want to identify, the n blocks by a kind of projection, sort of like you do on the torus with ZD. So for x and y and Hn, I'm going to define Jn of xy to be the sum over all of the v's that would project onto y. So, like if this was y, there'd be another y over here or something, like another y up there. Those would be the v's. And you can do that sum. And actually, you just get jxy plus a constant. So the hierarchical Laplacian on Hn uses this Jn in its definition. So minus the Laplacian is the identity minus Jn. And so you just put that Laplacian in here, and you've got your phi to the fourth model. Okay, the only place that the hierarchical part comes in is right here in the choice of the Laplacian. There's a metric on H infinity, which is just the distance from x to y is L to the jxy. So like the distance between 2 points in this block is L, and the distance between 2 points in this block and 2 points in that block, 1 point in this block and 1 point in that block would be L squared. The distance between this point and this point would be L cubed, and so on. And it's a computation that you can do that the metric ball of radius rho on H infinity with this metric contains order rho to the d points, and the green function, which is the inverse of the infinite Laplacian, the Laplacian on H infinity, decays like Euclidean norm of x to the minus d over minus 2. So these are properties that are suggesting that something like ZD is happening here. Now, here's a theorem about the phase transition in the hierarchical model. So I define this Gaussian measure, d mu ns. So n is where x lives in Rn. So it's an integral over Rn, and this is a measure on Rn, and it's proportional. Its density is e to the minus s x squared. So here's a theorem that was proved first for d equals 4 with Bauer-Schmidt and Bridges, and then subsequently for d greater than 4 by Mishna and Park. At first we thought that d greater than 4 should be vastly easier than d equals 4, but it isn't. So phi to the fourth in the terminology of the renormalization group becomes irrelevant for d greater than 4, whereas it's marginal in d equals 4. That suggests that it could be easier. But as Michael Fisher called it, phi to the fourth is a dangerous irrelevant variable. And we felt the danger when we tried to do d greater than 4. But we did anyway. So for d greater than or equal to 4, for any n, for g small, there's a critical value, nu c. So nu, remember, was the coefficient of phi squared, such that for a positive epsilon, as r goes to infinity, if you look at a nu which is a little bit above the critical point, so this is subcritical, then the total spin with Gaussian scaling converges to this Gaussian measure. And the susceptibility, the infinite volume limit of the susceptibility is given by the second moment of this Gaussian measure. And that's 1 over m epsilon squared, where this m epsilon, which is where the epsilon dependence comes in, is either epsilon for d greater than 4 or epsilon with a log correction for d equals 4, and that log correction depends on how many components your spin field has. So this theorem is also proved for Z4, but we're using it in the hierarchical setting. So here's a theorem about the plateau for the torus. We define a window scale, which is a multiple of r to the minus d over 2. So again, 1 over the square root of the volume for d greater than 4, with a log correction that depends on the number of spin components for d equals 4. And then this universal profile, which is related to the one that we have seen before. So e to the minus 1/4 x to the 4th minus that 1/2 sx squared is the measure. And we're looking at the second moment. And what we proved in a couple of papers is that for d greater than or equal to 4, any number of spin components, small g, the g is the constant in front of phi to the fourth, and for any s, real, as r goes to infinity, if we look at nu in the window about the critical point, so nu c, that's the infinite volume critical point, and we're looking at the, we're scaling away from the window with this wr, or from the critical point with this wr, we're in the window, that the total field properly normalized, which is not Gaussian scaling anymore, converges to this measure. Okay, so this is a vector in Rn, and it converges in distribution to this measure here. And using that, you can prove that the susceptibility in the window is asymptotically given by this profile times the square root of the volume with a log correction for d equals 4. The log correction doesn't depend on how many spin components you have here. And the two-point function has a plateau. So in the window, this is the finite volume quantity. This is gr means that we're in lambda, which has side length r, the hierarchical lambda with side length r, behaves like the infinite volume massless two-point function. So that decays like 1 over x to the d minus 2, plus this explicit profile times the plateau term, okay? 1 over the square root of the volume with a log correction for d equals 4. That's the same thing, isn't it? Yeah. So we claim that this profile should be universal. So here's the profile. And so we conjecture that it occurs in n-component spin systems defined on ZD, or on the torus. I mean, when I say ZD, I mean on the Euclidean model, not on the hierarchical model, for d greater than or equal to 4. And in particular, that F Ising that I showed you back when we were talking about the Ising model is just the one component profile. There's a sign change because the nu and the beta go in opposite directions, but it's the same profile. This profile, this function here, it has it looks like it's only defined for n equal, a natural number, but actually you can write it in such a way that it extends to all n real greater than or equal to minus 2. And in particular, it's defined for n equals 0. And for n equals 0, it's given by this formula right here. And, well, it's an old statement by de Gennes that from more than 50 years ago, that the n-component spin system with n equals 0 is the self-avoiding walk. And here, this profile with n equals 0 actually does match what we saw on the complete graph and what we conjectured for the Euclidean torus. Now, these results that for the hierarchical model, they have an exact analog with free boundary conditions. So I defined the hierarchical model to match periodic boundary conditions. There's also a way to do it with free boundary conditions, which is essentially to leave out that constant term in the J that came from summing over all of the representatives of our point Y. And what we found when you look at free boundary conditions is that you should take this nu C, which is the infinite volume one, and shift it by an amount VR to get the effective critical point for free boundary conditions, where the shift scale is given by r to the minus 2 when d is greater than 4, and there's a log correction for d equals 4 with the same gamma hat that shows up as before, depending on the number of spin components. In particular, the shift here, the VR, is bigger than the WR. And so what we're claiming, or what we proved in the hierarchical case, is that the behavior around the effective critical point for free boundary conditions in a window of width WR is the same as what it is around the infinite volume critical point with periodic boundary conditions. And those two windows don't overlap. And in fact, with free boundary conditions, if you look at nu C, we proved that there's a Gaussian limit. And so this is consistent with the Gaussian limits for ZD that are famously known for D greater than or equal to 4, from Eisenman and Froelich, and more recently with Eisenman and Dumenil-Copin. So there's no inconsistency here. Now, my last example is percolation for D greater than 6. So I'm looking at bond percolation on ZD. Nearest neighbor for D greater than or equal to 11. 11 is, has no significance as a number. It's just how far you can make the proof work. Or spread out for D greater than 6. Or spread out means you look at, you sort of enhance the graph by adding more bonds. So there's going to be a bond between any two vertices which are within a distance L of each other, where L is some large number. In that case, this L is very useful, and you can get down to D equals 7. So the two-point function and the susceptibility, either in finite volume or in infinite volume, but first I'm talking about infinite volume. The two-point function is just the connection probability for the probability that 0 is connected to x, and the susceptibility is the sum of the two-point function. And some years ago, it was proved that the critical two-point function, so this is at the ZD critical point, of course, it behaves like a multiple of 1 over x to the d minus 2. And what we did with Tom Hutchcroft and Emmanuel Mishta was we extended those results. And this, again, this is not a simple extension. This really requires new ideas and more work to get this near critical bound on the two-point function. So the near critical two-point function, so this is for p less than pc, or equal to pc, is bounded above by 1 over x to the d minus 2, so that's the critical behavior, times this, this factor, like we've seen before in other talks and also in this talk. So this 1/2 is the critical exponent nu. So that's the main input, and then with that input, we were able to show that in this case, throughout the entire window, so for any value of p which is within cube root of the volume, 1 over cube root of the volume of the critical point PC, either towards the supercritical or the subcritical, the two-point function has a plateau. So it behaves like 1 over x to the d minus 2 plus 1 over r to the 2d over 3. So the exponents are different here. It's connected with the fact that the critical dimension is 6 rather than 4. It changes some of these exponents, and so the 3's are coming in out of that. The susceptibility in this range is of order r to the d over 3. Now, the proof to get in, exactly to the critical point, which we couldn't do previously, this uses lace expansion results, and they don't work past PC. So how did we do that? Well, we added in some results of Kozma and Nachmias from 2009 and 2011 for one-arm exponents to reach PC and beyond. And there's a coupling of ZD and the torus. That coupling, it's present, for example, in the work of Heidenreich and van der Hofstadt. And the relevant diagram now turns out to be this one for the lower bound. I don't try to explain that, but this diagram has critical dimension 6, whereas these ones have critical dimension 4. If you do instead free boundary conditions, well, the upper bound is easy. The free boundary condition thing on a finite box is bounded above by the ZD two-point function. So we know that's 1 over x to the d minus 2. But Chatterjee and Hansen proved a lower bound, provided you stay away from the boundary a little bit. And the susceptibility behaves like r squared. So we see that the two-point function has a plateau for periodic boundary conditions, but not free boundary conditions. The susceptibility is larger for periodic boundary conditions than for free boundary conditions. And the reason is that the percolation cluster on the torus in high dimensions, when it wraps around, it finds new territory. So in low dimensions, this isn't going to happen because when the cluster wraps around, it's going to bump into itself again. But on the torus in high dimensions, there's so much space for d greater than 6 that it wraps around it. It'll keep on discovering lots of new territory so that the susceptibility ends up being much larger than if you didn't have the wrapping. Now we have a conjecture so I'll finish with this, that for d greater than 6, based on related results for the complete graph, work of Aldous and Janssen and Spencer, that there is again a profile, a universal profile. But this one is complicated, unlike the simple sort of 5 to the 4th type functions that we were seeing before. This one's complicated. I don't know if it has a simpler representation, but essentially what I'm saying here, and I see I left off an important factor here. So this 2-point function in the window on the torus is given by the torus, the ZD 2-point function plus this f perk, and there should be a 1 over r to the d over 3, which I forgot. Or is it r to the 2d over 3? Yeah, there's a factor missing here. What's really important is what I want to emphasize in the conjecture is that there's we have an idea what the profile should be. So it's given by this formula. F is something simple. It interestingly involves an x cubed. In the physics literature, percolation and phi cube theory are related to each other in a way that has never been understood mathematically. And then there's this complicated function here, which is a moment generating function for the area of the Brownian excursion. And based on what I was saying earlier about periodic versus free boundary conditions, we think that the same thing would happen if you replace PC by PC plus VR, where VR is r to the minus 2 if you were working with free boundary conditions. There are other examples, so lattice trees and lattice animals for d greater than 8. With Yucheng, we're working on something there right now. It's actually helpful to see these models with different upper critical dimensions, 4, 6, and 8, because then you start to actually understand what a unified picture of it could be. There's another example, loop erased random walk, which was studied by Benjamini and Cosma on the torus. The focus there is somewhat different. And I'll just end with a few references for the kind of things that I've been talking about. And thank you for your attention.
Questions?
So on a hierarchical lattice, you were taking an n-component model.
Yeah.
Do you expect that if you just started with a supersymmetric model, you could just take n to be n down to the minus 2, or?
Yes. Yeah, n equals minus 2, not so interesting because it's a Gaussian model. So it's just a Gaussian because, yeah, it's just a Gaussian. But n equals 0, yes, I think you could do self-avoiding walk that way. And there is a rigorous identity that relates the self-avoiding walk 2-point function to at least the weakly self-avoiding walk 2-point function to a supersymmetric spin model. That's what Yucheng used yesterday. N equals minus 1 is somewhat mysterious. I've seen papers in the physics literature that say it's related somehow to loop erased random walk, but I don't understand what's going on there.
And why is it that you can't go below minus 2? Like the spin system makes sense.
Yeah, the profile doesn't, it doesn't extend, so. I can't give you a reason. You just write down the formulas and you see how far you can go. There's an n. There's an n plus 2 somewhere in the denominator. Yeah, Felix.
So you contrasted the free boundary condition and the periodic boundary condition. What for instance, if you take a box where, let's say, 2 of the faces are periodic and the other faces are free?
Yeah, so you could try to look at mixed. We didn't do that. I think you would need to have your periodic boundary, your periodic components to be at least the upper critical dimension in number. You know, for the difference to take place, because it's from this wrapping thing that I was talking about, and you need enough space for that wrapping to be significant. Peter?
In your result for easing, for instance, in dimension 4.
Speak up, please.
Sorry. In your result for easing dimension 4, where you have the plateau for
The conjecture for dimension 4.
Okay, maybe it's a conjecture. So then maybe that's another conjecture. When you make it a little bit long range and you can go a little bit below dimension 4, I mean, is this plateau phenomenon supposed to persist, or does it go away because of the long range?
I haven't considered that question, so I don't really want to give an answer to it.
So n equals -2 is Gaussian, of course, so you're saying the profile does match.
Yes, yeah, right.
But there's many versions of n equals -2, of course. You can keep adding extra boson field and fermion field and keep getting -2. And actually, loop array random walk can be thought of as n equals -2 in that sense.
I see.
So,
Okay.
so it's not obvious to me that you always get the same profile, even as you change the way you write n equals -2. Have you checked that?
I haven't really thought about n equals -2 except to observe that the profile breaks down at n equals -2.
Well, you included -2 though, so I'm just talking at -2.
Yeah, so I know what the profile is there, but I don't know what it's related to. Right?
But,
I've only checked n greater than or equal to 0.
but your first example was simple random walk, which presumably should have n equals -2.
Does simple random walk have n equals -2? Oh, you mean because it's Gaussian?
Yeah.
Yeah, I don't know.
Okay, so I think we should probably refer further questions to lunch. Thank you